Okay, so here's the deal. So for number 13, we've talked about the fact that there are two ways of finding torque, right? Torque is the magnitude of your force times the length of your lever arm, assuming everything's perpendicular, right? And we've talked about the fact that you can find torque by doing I times alpha, right? And usually your I is some fraction, B, we've been using, right? Times mr squared, right? So far in all of the problems that we've done, the force producing the torque has been exerted at the outer edge of your object, which means that for all of our problems that we've done so far today in class, the length of our lever arm has been equal to the radius of the object. And that's not always true. Okay? So like this door over here has rotational inertia, yes?
Yes.
Okay? And based on this little sheet here, which shape is the door, you guys? This is going somewhere, so bear with me here. Which one of these shapes is a door?
The fourth one.
This one, right? Okay. So notice the rotational inertia depends on the mass of the door and on this dimension of the door, right? Which I would call the width, despite the fact that the drawing has this one labeled as W. Good?
Yeah.
All right. So look. So that door over there has a rotational inertia that is dependent on its mass and this distance, right? Okay? But suppose I come and from inside the door, suppose I push, so right now I'm pushing here on the door. Is my lever arm the full width of the door?
No.
No, because my force is being exerted here instead of out here, right? Does that make sense?
Yeah.
So it is not always necessarily true that this lever arm here has to equal, oh my gosh, this lever arm here has to equal this radius, all right? And number, whatever I said we were going to do, 13 gets at that idea, all right? So with that in mind, here we go. So in number 13, we already did part A. And again, everybody was good with A? All right, so in part A, what happens is Joe slams this door, all right? So he just like winds up and pulls it shut, all right? So here's the door. All right, and at the end of part A, you had to find the door's final angular velocity. And what you found was that that angular velocity, after Joe lets go of it, is 11.5 radians per second. Cool? All right, other things that we know about the door is that the door has a mass of 30 kilograms, and the length of the door is 0.65 meters, or the width of the door, whatever you want to call that. So that's what's happening at the end of part A. Then B says, poor Mitch, the door smacks into his nose just before closing. His nose hits the center of the door and compresses 1 centimeter before stopping the door. So the idea is, I'm going to exaggerate this drawing a little bit. So here's Mitch, top view. Here's his eyeballs. This is going to be a weird drawing, I apologize. We'll give him like cartoony eyes, all right? And he's got a big Pinocchio nose. Okay? Okay, notice where his nose is hitting. It's hitting the center of the door, right? Okay? And so the idea is, as the door comes to a stop, it squishes his nose 1 centimeter.
Doesn't that break his nose?
Yes, it absolutely will break his nose, 100%. Okay? And so the idea is, by the time the door gets to here, A, his nose is broken, B, the door is now stopped. Does everybody understand what's going on there? Cool? All right, so let's do a couple things that hopefully you had already done. So we already know the rotational inertia of the door. Does everybody understand that it's the same as it was in part A? It's the same door. It has the same mass, the same radius. The fact that the forces on it are different doesn't affect the rotational inertia. Is that clear, you guys? Okay. So if you find that rotational inertia, it was 1/3 mr squared. So it's 0.65 squared times 10. So it gives you 4.225. kilogram meters squared. All right, so there's our rotational inertia. All right, and the question wants to know how much force does Mitch's nose exert on the door? All right, and the important thing to notice is that this force is not being exerted at the outside edge of the door. It's being exerted here, at the center of the door.
This isn't like, could you solve it like doing like a work problem or no?
No, I'm super glad you just asked this. Shoot, I wanted to talk about it on another problem.
Because I like, it looks like a work problem.
So you're doing force times distance?
Yeah.
Oh, you know what? Actually, I'm lying.
Work? Do you want me to just do it?
No. I want to finish it the way that I had in mind. But you know what? You might be right. You could find the change in rotational kinetic energy and set that equal to your work. And your work should be force times distance. I think that will work, actually.
And distance is just how you would have
Is
to
the 1
use
centimeter.
trig to figure. Oh, well, how much how much the door went like up.
Force times distance. The nose is exerting some force
Yeah.
through a distance of 1 centimeter. So I think that would work, actually.
So when you said you wanted to talk about a different problem, what?
That was a separate issue.
Okay.
Let me come back to that and
Okay.
remind me when I'm done. Okay, so is everybody good up to here? All right, so if I want to do FD equals I alpha, I got to find my alpha, right? Does everybody agree with that? So here's what I know. I know my initial angular velocity is 1.5 and my final angular velocity is 0. What is the 1 centimeter, you guys? And you can't just say distance, because there are 3 different distances in this problem, right? So let's identify what the different distances are. There's r, which is the 0.65 meters. That's important because we're going to use it to calculate our I, right? As in I equals 1/3 mr squared, right? Okay. Is the 1 centimeter the length of my lever arm? Force times 1 centimeter, is that right? No. When I do torque equals force times distance, what's the length of my lever arm going to be? Or how would I find it, maybe, is a better question. How long is the lever arm in this problem, you guys?
Isn't it just like whatever his nose minus 1 is?
Mm-mm.
Good.
Good. It's half of 0.65, right? Because my pivot point is here, and the force is being applied out there. So that little pink line that I just drew there is the length of my lever arm. Okay? So my D is half of 0.65, so that's 0.325 meters. I'm going to use that to calculate my torque, as in torque equals FD. Cool? All right, so we still have to figure out what the bleep that 1 centimeter is. So Hannah, you had your hand up a minute ago. Did you figure out what the 1 centimeter was?
Yeah. Is it stopping distance?
Yeah, it's stopping distance. It's the displacement. This point on the door is going to go through a linear displacement of 1 centimeter. Follow? So, how can I use all this garbage to find the alpha? It's 2 steps. One of those steps has got to be a jumper, right? So, we know our angular velocity. We're looking for our angular acceleration. Do we know the time? No. So there's got to be something else we can use.
It's the delta theta.
Yeah. Can't we do this? Delta theta, and then use the jumper with our delta x? Now, be careful. Like historically, it's always been divided by r. Do I want to use r here, though? Do I want this full r? No, I want this r, which we actually have called d in this problem, right? So it's over d for this problem because the radius for that part of the circle is only half of our radius. Follow? Okay, so it's 0.01 meters over 0.325 meters, and it gives you 0.3, that's wrong, don't write that down. 0.01 divided by 0.325, it's 0.03077. What are the units going to be here, you guys? Radians, right? Follow? So now we can use this guy find our alpha, because we know our delta theta, our omega I, and our omega F. That's highlighted, not crossed out. Yes, Wesley?
So if you're just solving it the work way, you just do change total energy.
Let me come back to that, because I don't think that's the way most people probably thought about
I
it.
have a tutorial during class time just talking about it.
Great.
Okay.
All right. So solve for your omega, or solve for your alpha. So let's see if this works. We got 11.5 squared divided by 2 divided by our alpha. And it gives you 2,149 radians per second squared. Everybody good? We're almost done. Any questions before I go on? All right, let me clear up a little space on the board here. Oh, darn it. All right, so now let's see. We can find our torque. Net torque is I alpha. So our I we already found. Our alpha we just found. It's 2,149. So multiply that out, and our net torque turns out to be 9,080 Newton meters. Good? Okay, so last step, now we got to find the force, right? So this is the part that I wanted to make sure you were aware of. When I do this last step, that works. I'm going to go, oh, well, net torque is force times distance. So I just found my net torque. We're looking for the force. What do I use for my distance? Hello.
Is there Sophia in here?
She's not here.
Okay, thank you.
Yeah. So what do we use for the distance, you guys? What do you think? Weston said 1 centimeter. What do you think?
1 centimeter sounds good.
Remember, when you use this FD, it's always the distance between the force and the pivot point. So on this drawing, where is the pivot point? That's my pivot. That's my pivot point. Right? My force is being applied here, right? So this length here is my D. We already wrote it down. It's this 0.325, right? Okay?
Did she come to class at all?
No. In fact, she was also on the... No, she wasn't in third hour either, is my understanding. I think she was at the start of third hour, but not the end. Good? So then divide, and your force ends up being, it's pretty close to 27,000 newtons. Is that wrong?
No, it's 27,938.
Okay, yeah.
Yeah.
Oh, I guess it's almost 28,000, isn't it? All right. Are we good, you guys? I think that's about as hard as they get. So if you can do that, you're in pretty good shape. All right. Moral of the story is please make sure you keep track of all your distances. There are a lot of them. And that can be, I think that's the most confusing part of all this, is figuring out which distance to use when. Okay? I, the mr squared thing, is always the radius shown on the sheet. So you got to look at the drawing to figure out which r you use when you're calculating your I. So if you're doing, a rod, then it's the length of the rod. If you're doing a rod pivoted about the middle, then it's half of the length, etc. Okay? For your torque, it depends on the distance between the force and where your pivot point is. Cool? Questions, issues, concerns, anything? All right, so tomorrow we're going to do a target check on this stuff. And then we're going to get for 7 years.